So I'm going to introduce the speaker today. I'd first like to thank Len for giving me the honor of introducing our speaker, Dr. Nader Engheta. I've known Nader since I was a first-year graduate student, and you had just started your academic careers that year. I won't give the date away, but you can probably tell by the color of our hair that it wasn't recently. Nader, I'll give the details. He received his bachelor's degree in electrical engineering from University of Tehran and a master's and Ph.D. in electrical engineering from Caltech. After spending a few years in industry, he joined the faculty at the University of Pennsylvania, where he's currently the Nedwill Ramsey Professor of Electrical and Systems Engineering. One of the things that I admire the most about Nader is he's truly an innovator. It's incredible. He continually comes up with new ideas that really take technology and science to the next level. He's made fundamental contributions to a wide range of scientific areas, including metamaterials, plasmonics, nano-optics, antenna theory, and even the understanding of the visual system of fish, one of my favorite. Nader's had way too many honors for me to list all of them, but I'll embarrass him with a few. He's been selected Fellow of the American Association for the Advancement of Science, Fellow of the American Physical Society, Fellow of the IEEE, Fellow of the Optical Society of America, Fellow of the SPIE, and a Guggenheim Fellow. He's been awarded the IEEE Third Millennium Medal and the 2008 Georgia Heilmeier Award for Excellence in Research. That Penn only gives one of those per year. He's a Fulbright Scholar and an NSF Presidential Young Investigator. And the number that kind of blew me away is for all those academics, his H-index is 44. And he has over 20 papers with over 100 citations. I think that tells how far-reaching the research he does is. My personal favorite is Nader was selected by the Scientific American magazine as one of the top 50 leaders in science and technology, award really well-deserved. As a former student, what makes his scientific achievements all the more remarkable to me is he's equally gifted as a teacher, a mentor, and a friend. So with that, can you help me welcome?
Thank you. Thank you very much. Thank you very much, Mark, for this generous introduction. It's a great pleasure to be here. You can hear me in the back. Yeah. It's a great pleasure to be here. In fact, University of Delaware is just like my second home. I've come here often. In fact, we have many friends, Dennis Prader, Mirosnik, Mike Haney, and Dan Weil. In fact, Dennis and I had grants together. We had joint projects together. So it's a pleasure to be back here and to talk to you. And I want to thank Len Semini, another good friend of mine, and Mark Mirosnik for giving me a chance and for the invitation to be here. What I'd like to talk about today is one of the areas of research activities in my group, namely the areas of metamaterial and plasmonic optics, and to see how we can use the concept of metamaterial to bring the fields of electronics, photonics, and magnetics together. And under this umbrella of commonality of these three fields, which I like to call it the unified paradigm of Metatronics, and you're going to see why we name it that way, we're going to see how we can come up with some interesting ideas for future devices and components. But before I get into the motivation and the specific topics that I'd like to talk about, let me show you one slide of other areas of research that's going on in my group, so you can put this in perspective to see what's going on. In my group, we are interested in the physics and engineering of fields and waves, particularly electromagnetics and optical fields and waves. And under this umbrella of research interest, we have several research programs that's going on currently, my group. One is the area of metamaterial, some of which we're going to talk about today. And that is the material in which you can design the material in order to give you specific properties. By that I mean electromagnetics and optical properties that you would like to have that not necessarily easily accessible in nature, but of course physically realizable. Another area is plasmonic optics, and that is optics at the nanoscale, how optical wave interacts with the nanostructure, and this, of course, nicely connected with this area as we go to the shorter wavelengths in metamaterials. Antennas have been of interest to me since I was a graduate student. In fact, I was talking to some of you mentioning how I started actually in antenna through the radar system. And then we are still interested in antennas, but particularly taking them into the nanoscale, the optical antennas, how we can actually have nanostructure as optical antennas. Recently, in the past 2 years, we started a new program on graphene metamaterials, how to bring the two fields of graphene, which is one atom thick, structures and metamaterial together, particularly in the mid-IR, region. And connected to this, if I get a chance at the end of my talk, maybe for a few slides, I'd like to talk about another area that we have begun, and that is control of the direction of a flow of photons, and that is for the non-reciprocal type of structures that would nicely connect with the other areas. Mark mentioned about the areas of interest that we have in polarization vision in nature, and that's the area that actually has nothing to do with the metamaterials, and that started with the collaboration I had with a colleague in the medical school many years ago, you remember, at PU. And we wanted to see actually how we can learn from the visual system of animal species in nature and develop camera system that would see the world different from the way that human eyes can see. And I'm not going to talk about those at all today, but if anybody is interested, I'd be more than happy to talk to you about the area that regard. And extreme parameter metamaterial is another thing that nicely connect to the other areas. In my talk today, we're going to concentrate only on bits and pieces of some of this, but I'd be more than happy to talk to any one of you offline if you're interested. But before I get to the gist of the problem that we would like to talk about, let's talk about motivations. Now, if we look at the history of science and engineering, usually when the field is at certain level of development, then certain modularization, parametrization, and characterization actually help accelerate the development on the field. What do I mean by that? If you look at the system approach, you're going to see that often, sometimes knowingly, sometimes unknowingly, we try to modularize system. We try to parameterize the system and standardize. Now, I'm going to give you 5 examples. Before I get to our main topic, I'll give you 5 examples. 3 of them we are very familiar with that. All of us are very familiar with this. The other 2 we are also familiar with that, but less obvious. So what do I mean by modularization, parametrization, and standardization? Very good examples, electronics. If you look at the field of electronics, this field has seen fantastic development in the 20th century and continues to evolve in the 21st century. Why? I mean, what are the reasons behind the success of electronics? Many reasons. In fact, we can't think of life without electronics these days. Without electronics, we can't even do anything. Now, but why is it that electronics is so successful? From a physics point of view, it's successful because you can control the motion of charged particles. By putting an electric field, electric charge, you can move it the places you want to go. But from the system point of view, one of the main reasons that this electronic field has been so successful is the fact that we can modularize the field. We can have lumped circuit elements. I mean, you go to Radio Shack and you buy resistor, capacitor, and inductor, and that's already modularized. So it's become like an alphabet of a language. And what you need to do in a relationship between voltage and current of that module. And after that, you can just connect them together. I mean, this simple concept, but very powerful concept, has helped the design in electronics very, very powerful. We take it for granted, but when we teach our students, the first course in circuit, we teach them this. And after that, they put them together, and you have infinite number of possibilities. Your cell phone is a good example of that. So that's, of course, a very obvious example. I come back to that later in my talk. Another example of simplification and modularization in signal processing. Analog versus digital concept. This is, of course, very obvious to all of us. If I have an analog signal, I have a lot of information there. But we simplify that, we lose some of those information in favor of simplicity. So we deal with a digital signal instead, zeros and ones. And Boolean algebra help us to actually develop that field. And so digital system, even though it's simpler, is actually more powerful in some sense. And of course, digital electronics has been around, and we know that works so nicely. How about another example of simplification and modularization? Well, smartphone that many of us have. Steve Jobs recently passed away, but one of his vision was simplicity. Simplicity doesn't necessarily mean approximation. Simplicity means modularization. If you look at your iPhone, for example, those of you who have iPhone or any sort of smartphone, you notice that we have icons over here. And icons, in fact, is modularization. Because if you like to know the temperature of the day, you just touch that icon that has the word temperature in it. You don't write a code of computer every time you would like to actually find that temperature. Somebody else has done that for us. So that modularization helps us a great deal. Now, many of you are young, but some of us who have been around a few more years will remember that we used to actually use the DOS like this. And in fact, I was talking to some of you, you mentioned that we still continue to do that, as we were talking about. Now, what did it take for the computer to get from here to here? Many reasons, of course, many innovations, but one of them is the issue that you can actually modularize. You can actually make block system. These three examples, by the way, we are very familiar with that. But let me give you two other examples, some of which would be less familiar with that, but necessarily as powerful. Information theory. Now, Claude Shannon was one of the guru of the information theory. If you have a transmitter and receiver and you're connecting that to a noisy channel, that was actually a very, very important problem many years ago. How to model that, how to conceptualize that, how to modularize that. And what Claude Shannon did is came up with a very simple formula, very simple conceptualization of that, channel capacity. And that actually started a completely new field of information theory. And the rest is history. A lot of innovation came out of this, simplification and conceptualization. But the fifth example is less obvious, but it's closer to my heart. And that is the development of antennas. Now, many of the gadgets that you use these days have antennas. Well, where does the history antenna come from? In 19th century, Heinrich Hertz, Oliver Lodge. These giants actually came out with this concept of antennas. But this concept, by the way, at the time, nobody could predict that it would have fascinating application. In fact, there's an interesting quotation, I'm paraphrasing, that they ask, Heinrich Hertz, Mr. Hertz, do you have any application in mind with what you do over here for this structure? And he said, absolutely nothing. The only reason I do that is to prove that Master Maxwell was right, and we do have electromagnetic waves. But of course, we know these days that everywhere we have antennas. So what did it take, again, to come from here to here? Now that we are really indebted to several giants in the 20th century. Professor R.W.P. King from Harvard, Dr. Sergei Shelkonov from Bell Laboratory, Pocklington, Hollane. These giants, what they did, they worked tremendously in the theory of antennas, but in particular, they did very, very interesting thing with introducing one simple number, input impedance of an antenna. So if you look at this monstrosity over here, which we have to solve every time we have an antenna, yes, that's our job in electromagnetics, we solve that. But what's really important is this entire monstrosity is simplified through one complex number as you look into the port of the antenna. And that complex number actually helped a great deal to connect the concept of antenna with the rest of the circuit. Imagine every time you wanted to actually connect an antenna to circuit, you had to solve the boundary value problem, including the circuit. That would have been tremendously difficult. We still have to do that sometimes. But with introducing, thanks to these guys, with introducing this concept of input impedance, that simplified the field and tremendously accelerated the field of antennas. That's what in 20th century, antenna became so powerful, and every piece of things that we do deals with the antenna, more or less. On a personal note, by the way, I'm fortunate that I got to know Professor R.W.P. King personally, because he was the professor of my professor. So when I did my PhD at Caltech with Professor Pappas was his student. And he was an amazing guy, by the way. He recently died at the age 100. He wrote his last paper at the age of 97 or 98, a single author paper. Guess about what subject? Dipole antenna. And so he wrote books about antennas, but still he had a paper at the age 97 or 98 to write about this. Fascinating man, participated in conferences to the last day of his life, sitting in front and arguing, and health-wise he was very good. The only thing was losing a little bit of his hearing, but other than that, he was wonderful. Great, great person. So, the question I want to pose is that with all this modularization and conceptualization, one of the things that we have been interested is to see whether we can make the field of nanophotonics modularized, parameterized, and actually simplify that. Because we believe that if we do that, we can actually accelerate the development of that field. In order to answer that question, let's go back to the basic. The interaction of light with matter, by the way, as you know, is governed by the laws of electrodynamics, both classical and quantum electrodynamics. And in fact, we already do some modularization when we deal with bulk material parameters. Many of you are familiar with that. Permittivity, permeability, conductivity. nonlinear susceptibility, chirality. All of these actually represents a bulk property as a whole in the macroscopic scenario. But what we would like to do is, in fact, to do this modularization even further, not just at this level. It's interesting that these parameters, of course, have certain range in nature. Nature has provided us tremendous list of materials, many of which you're familiar with, periodic table and the material that we can see in nature. But the concept of metamaterial in the past several years have actually opened up an interesting possibility. How to actually design a material by putting inclusions into a host medium. So the concept of metamaterial is actually a relatively simple concept. If you have a host medium and you embed this medium with many man-made inclusions, this could be mesoscale, microscale, nanoscale, depending on the wavelength of interest. And if you have electromagnetic wave propagating through it, you're going to have induced electric and or magnetic dipole moment at these inclusions. And then when you look at the combination and bulk of these dipole moments, effectively, you can actually look at this material as a bulk material. And that effective of this induced dipole will give you an effective permittivity, effective permeability, or effective index of refraction. Now, nature has done that through atomic structures. Metamaterial is doing that through geometrical structure, or structural things that you put over here. But because these are man-made inclusions, you make them, you have control over these scenarios. You have control over their compositions, arrangements, density of them. So all of these are under your control. So you have a lot of knobs to turn in order to design the properties of this material. In the past decade, 11 years, basically, there are many, many activities in metamaterial going on. Here, I just show you a collage of a sample of metamaterial that has been made by many experimental groups all over the world. This sample, of course, is not exhaustive. There are many, many groups working on metamaterial. I'm just showing bits and pieces of some of the results of many experimental groups. One thing you notice that as the time goes by, this inclusion becomes smaller and smaller and smaller in size. It started with microwave, and now we would have in nanoscale structures that you have there. Now, if you look at these material parameters I show you, like permittivity, permeability, and those guys, you can categorize them in a different way. Of course, sometimes we categorize them based on the group theory, the group symmetry. Sometimes we categorize them based on their physical properties, electric properties, magnetic properties, and so on. But in this slide, I would like to categorize them differently. I would like to say that these material parameters, I'm going to go over the list of them, each one of them actually is responsible behind the development of certain technology. Let me tell you what I mean by that. So let's start with conductivity. Conductivity, in my opinion, is responsible behind the field of electronics. After all, in semiconductors, we are after controlling the mobility, which relates to conductivity. We use wires, we use transistors, we use elements there. So effectively, what we see over here is the three-dimensional inhomogeneous distribution of conductivity. You can think about it that way. That's what the electronics effectively is. How to control the motion of charged particle, how to control the mobility. So we can categorize it that way. So in some sense, I can look at this circuit board and I said, this is also metamaterial. But it's metamaterial based on the distribution of conductivity, for example. If you look at permittivity, or index of refraction, is responsible behind the field of photonics and microwave. In fact, if you look at an optical system, you can interpret that as a three-dimensional distribution of index of refraction. Effectively, that's what it is. How about permeability behind the field of magnetics? How about nonlinear susceptibility behind the field of nonlinear optics? How about chirality behind the field of optical activity and stereochemistry? So every one of these parameters, by the way, have been really the workforce behind these technologies. But if you look at the history of development of this technology, you notice that most of these technologies or field areas develop on their own, basically, independent of each other. Electronics, had their own history. Photonics had their own history. Magnetics like that, and so on. But the question we have been interested is to do the following. After all of this follows Maxwell's equation. So why don't we actually try to make these fields develop and evolve together? Not necessarily separate with each other, but actually evolve them under one umbrella and treat them all in a similar way. Of course, the physics of many of different things are different, but keeping that into account, we may be able to come up with interesting innovation if we change our mindset about the development of this field in the future. Now, what do I mean by that? So one of the things I would like to show you, mostly for the rest of my talk, is to see what would happen if we look at one example. Can we merge the field of electronics with the field of photonics and microwave? And I don't mean, for example, the electro-optic effect. And I don't mean no optoelectronic effect. I don't mean that. I mean, really, fundamentally, we look at these fields with the same mindset and to see what we can actually come out of this overall mindset. And in that case, concept of metamaterial can help us. So we're going to show you that actually, indeed, we can actually marry these two fields together using the concept of metamaterial, which I call the name of that area Metatronics. Metamaterial and tronics, electronics, photonics, magnetics. Now, this is not a one-way street. If concept of metamaterial can help us to have new paradigm for circuit, can this new paradigm help us to have new metamaterials? Because it can go both ways. If I can actually use that concept to have the circuit element, how can I use this circuit element to make new materials? So you're going to see what I mean by this two-way street that we have over here. So in order to do that, let's go back to the slide I showed you a few minutes ago. In electronics, we have modular blocks. Everyone is familiar with this one. Resistor, capacitor, inductor. As I mentioned, we take that for granted. But these are very, very powerful and at the same time simple concept. Why? Because if you actually look at the capacitor, the only thing you need to know is the relation between voltage and current at this capacitor. Every time you want to design something, you don't need to know what's going on inside the parallel plate of this capacitor. Someone has already done it. Once you have done it, and then you know how the system works. In that case, just like the alphabet of a language, these would be alphabets or this language. Why? Because you can put these alphabets next to each other and you have words, paragraphs, sentences. That's what we do in electronics. You basically put these elements next to each other and you have infinite number of combinations. But what is the building block in optics? The building block of optics is not what I showed you the last page. It is indeed waveguides, mirrors, diffractions. Dennis, this would be similar to what you have done, just like from your things, and from Dennis Prader's group, and lenses. So these are building blocks of photonics. These building blocks are very different. Why is that? Because historically, when they were building mirrors and waveguides, they were much bigger than the wavelengths. They couldn't make it that small, 100 years ago. But now that we can actually have nanotechnology that we can make these elements much, much smaller than the wavelength, it's possible to actually marry these two alphabets together. So here what I mean. The same way that in electronics you have lumped circuit elements, could we think of nanostructures over here that would be very small compared to the wavelength of light or wavelength of operation, whatever the wavelength you have, and it acts as lumped circuit elements. In other words, I can modularize them. I can say that, okay, this nanostructure would have this optical impedance. And if I can do that, can I put them next to each other and have a new type of circuitries? The answer is yes, we can do that. And in fact, we started this concept back in 2005. Back in 2005, we started this concept by saying, okay, imagine that you have nanoparticles, very small compared to the wavelength, and make of different materials, and we showed theoretically, and then using computer simulation, and just recently using experimental verification, which I'm going to show you, that indeed that's the case. So if you have a nanoparticle that's made of material with the permittivity with the real part positive, we show that this nanoparticle has an optical impedance that's similar to the optical impedance of a capacitor. Now, what is that capacitance? I'm going to show you in the next slide. What's the value of that? Inductor was a hard one. They always taught us the inductor is a piece of wire that you would do like this, send the wire to this, you get the voltage. But what you need in the inductor is a impedance that resembles of inductor. You can get that impedance in nanoscale differently. What if you have a particle that has a material with real part of epsilon negative? That will give you an optical impedance that resembles the impedance of an inductor. We're going to see that. Now you might say, do I have a material in which the real part of epsilon negative? Yes, nature has been nice to us. Noble metals, silver, gold, aluminum, platinum, they have permittivity whose real part of epsilon is negative. in the visible and in the near IR. So that's good. And the resistor is the easy one. That's the one that material has loss. And of course, every material has some loss, so imaginary part of epsilon non-zero. Now you might say, okay, very good. So these act as my lumped impedance at optical frequency. What value am I talking about? How big is this capacitance? How big is this inductance? So let me share some numbers with you. As engineers and scientists, we would like to see numbers. Imagine that you have a glass nanoparticle, let's say with a diameter of 60 nanometer, and you're illuminating the helium neon laser of 633 nanometer. If you do the calculation based on our recipe, you'll find out that this optical capacitance would be few attofarad, 10 to the minus 18. I would like us to actually take a note of that number. In a regular electronic, usually the capacitance is picofarad. This is 6 orders of magnitude smaller. That's actually a good thing. Let's hold on to that. Now, if I have a silver nanoparticle, remember silver has a real part of epsilon negative, you find out that that would give an optical impedance, just like a lumped element, that would be equivalent of an impedance of an inductor that is few femtohenry. Again, very, very small number, 10 to the minus 15. A regular, if you're in an electronic, then the inductor that you use is usually nanohenry, another 6 orders of magnitude smaller. So you might say, well, what is the significance of this hugely, very, very small number? Well, there are several advantages. Let me just share with you 2, 3 of them in the interest of time. First of all, we all know in electrical engineering that if you have a circuit, what is the bottleneck of the speed in that circuit? RC time constant. If we can make RC time constant smaller and smaller, circuit would respond faster and faster. We know that. Now, that's one of the problems we have in the chip of the computer, that if we make this thing smaller and smaller, then the wires become closer and closer to each other. Capacitance would not be that small, so there is a limit on the RC time constant. But here, C is 6 orders of magnitude already smaller. So the RC time constant in this circuit would be extremely small. In fact, we have done the calculation, and I don't have time to show you over here, but this circuit can respond to few hundred attosecond pulse. In other words, one cycle of the optical pulse can go through this with almost no distortion. That is really fast circuit. That's number one. Number two, if you go to Radio Shack and buy an LNC, and you connect them together, what do you get? You get a circuit that oscillates. The second order circuit oscillates. So if this acts as a capacitor and this acts as an inductor, what if I put these two guys next to each other? Better yet, what if I actually make a core shell structure that chemists can do very nicely with the core shell structure? That means what? That means this L and this C next to each other, or this L and this C next to each other, it is your RLC circuit at the nanocircuit. So yes, a core shell structure is RLC circuit at optical frequency. Now, also they taught us that if I have an L and C connect to each other with L and C, what is the resonant frequency with a simple circuit formula? Omega is equal to 1 over square root of LC. Now put these values of LC in that formula, you find out that resonant frequency becomes a visible light. So yes, this is an oscillator with the oscillation frequency at the visible light. This is RLC circuits we have. Now, in electronics, what we do is that when we want to have an oscillator, you connect RLC together. But of course, you have loss. So this oscillation die out. How do we keep them from dying out? You put an amplifier there, like an op-amp. So you keep the oscillation. So that means if I come over here and I put a gain material over here, effectively, if I can compensate that loss of that, I will have a light source that actually oscillates, just like what electronics would do. And that becomes a nano laser. And in fact, recent development by Professor Noginov from Norfolk State University in collaboration with the Cornell and with Purdue, they indeed have a core shell structure that actually lased. And that was a nano laser. Indeed, one can interpret their nano laser as basically an RLC circuit that oscillates, very similar to what you do in electronics. So when you actually have this mindset, you can actually do a lot of interesting things. Bring the electronics into the nanophotonics. So you might say, okay, so what? This nanoparticle acts as RLC. What good we can do with that? What I want to do is that for the next few seconds, I would like to imagine that all of you are circuit designer. How does a circuit designer design a circuit? Let's say a simple tank circuit. How do we do that? We go and look at the textbook, handbook. You look at the formula for the bandpass filter, for example. You would like to have specifically at this frequency to have certain bandpass filter. Based on the formula, you find out what RLC do you need. And then what do? You go to Radio Shack. You buy some of this. Actually, Radio Shack doesn't sell this anymore, so you just buy it online. And you come to the lab, you put them together, and then you test them, and you compare that with the circuit formula, and those circuit formulas have been around more than 100 years, and most likely you have the right answer. But in nanophotonics, when we want to design a filter, we usually do not do it this way. Why not? Maybe we can do it this way. So that's exactly what I would like to suggest. So if we want to do the same thing in nanophotonics, imagine I would like to have a tank circuit in the nanophotonics that would do this bandpass filter. So why don't I use the same law that I just said? Go to the circuit formula, find out what frequency you want to have there, find out what RLC do you need. When you do that, you find out the value of this RLC is not the one that I showed you in the previous page. It's the one that I showed you several slides ago. In other words, you're talking about femtohenry. You're talking about attofarad and so on. In that case, you cannot go to Radio Shack to buy those nanoparticles. What do? You go to the nanofabrication laboratory. And you try to nanofabricate this particle. That becomes your electronics store. But that becomes an optical store. It becomes optical elements. So you do that nanoparticles, you put them next to each other, you illuminate them, it should work. Like what we have as a filter. Different mindset, but you get the filter. In fact, in some cases, you can combine the two materials into one particle, because depending on real part of epsilon, imaginary part of epsilon, you may achieve both of them in the same particle. So we wanted actually to do this experimentally, to show that. And I'm going to show you the experimental result in a couple of seconds. But before that, let me show you one interesting theoretical observation first, two theoretical observations. So we wanted to see first, theoretically, whether that would be possible or not. So imagine I want to make this. I follow the recipe I mentioned, and I find that, okay, if I want to have C, I have to have a material with the positive epsilon, let's say silicon nitride. And if I want to have R and L, I want to have a material with epsilon negative and imaginary part there. So that would be silver. So I put these two nanorods next to each other, shine a wave through this, look at the transmitted wave versus the incident wave, try to find out the filter function. And here, I'm going to show you two theoretical approaches to this problem. First of all, this is the magnitude of transfer function, and this is the phase of the transfer function. The black curve, magnitude and phase, are actually results of the full wave solution to Maxwell's equation. You completely solve the wave problem. But the red one is a solution to the simple circuit formula. And look at the agreement. In this range, magnitude and phase agree nicely. Now, if you go to the UV regime over here, then the dispersion of the silver becomes, haywire, and the size of the particle is not small anymore. So you can't have it as a circuit. But if you have it small enough in this band, this looks like they agree together. So this was very encouraging for us theoretically. We wanted to see whether we can do it experimentally. But let me show you another interesting feature before I show you the experiment. And that is something that regular electronics does not have. Now, just like any analogy in science and engineering, it's good to start with analogy, but at some point, of course, the analogy will stop, and the two scenarios would have different things. Now, in a regular electronics, when you get an L and C, how do you connect them together? Either you connect them in series or you connect them in parallel. There's no third way, if you have two things. But in this type of circuit, in principle, you have infinite number of possibilities. Why? Imagine that you have a composite nanoparticle. Let's say half of it is metal, half of it is dielectric. The metal would act as an inductor, the dielectric acts as a capacitor. Okay, so this is an LC combination. But what kind of combination? Is it in series? Is it in parallel? That depends how you excite them. So if you excite them with a wave coming like this with electric field normal to that, that becomes in series. If you excite them with the electric field parallel to this boundary, that becomes parallel. So the same nanostructure acts as two different circuits, depending how you excite them. You don't need to change the material. Excite them this way, parallel circuit. Excite them this, series circuit. So, but what if you excite them obliquely? It's neither parallel nor series. It's something, combination and mixture of the two, which regular electronics does not have, at least to the best of my knowledge. So this gives us a very interesting concept, which I call it stereo circuit. So imagine I have a bunch of nanoparticles in the three-dimensional distribution. That means I can design this such that when I illuminate it like this, it may act as a bandpass filter. Illuminate like this, it may act as a bandstop filter. Like this, it may be low-pass filter. So the same cube can actually function differently if you illuminate them differently. And this is only just assuming that it's linear function. If you introduce nonlinearity, other interesting things can happen. You can bring this signal and that signal, you can mix them. And actually, we have come up with the design of a nano mixer, similar to the mixer you have in electronics, by actually combining a nonlinear material in this structure. So we wanted to actually show this experimentally. So what we did actually, we decided to actually design this nanowire. This is a two-dimensional version of that, so this is very long in that direction. But it's important to look at these nanowires, which is made of silicon nitride, with a specific cross-sectional dimension. Then we built 9 different samples with 3 different heights. For each height, 3 different W's width over here. And this height and this width are very, very small compared to the wavelength of interest, which is 8 to 14 micron. Now, the nanowires are very long in this direction, like 200 microns in that direction. So very, very high aspect ratio. Now, silicon nitride, by the way, has a resonance around 11, 12 micron. So if you operate near that, you have a real part of epsilon becomes negative. And of course, you have loss too. So this one should act as my inductor with the loss included as a resistor. And this gap is exactly the gap that we designed to have a capacitor. I mean, we could put another dielectric over here, which we are doing it right now in the different wavelength regime. So this effectively, when illuminated like this, should be a parallel RLC over here. But as I promised, in order to find out the filter function of this, I go to the simple circuit formula from textbook. See, this is the expression for the impedance of a simple capacitor. Just use that. And that becomes a parallel impedance, and from that you find the transfer function of this. Very simple circuit formula. So we wanted to do the experiment to see whether our experiment really supports this simple circuit formula. So that's what we decided to do. We built this structure on a combination of e-beam lithography and photolithography. It took us about 1.5 years to build this set. It was very challenging because we wanted to have this nanowire suspended. It started with the silicon on the base, we etched it from this direction and that direction. We wanted to have it suspended, and that actually took some time. Because sometimes we etch, early, we stop, and we have a thickness over here. Too much etching, break the wires. So after many, many tries, eventually we found the sets that we have, this thing suspend. Now, there's no need, strictly speaking, to be suspended, because if it's over the dielectric, I can actually have that as another circuit element. But I wanted to actually prove this very, very clearly, that these guys act as a lumped circuit element. So we did that, and we put it in the FTIR spectroscopy. And we illuminated with this electric field. So according to my theory, this should become a parallel circuit. And we illuminated like this. This should become a series circuit like this. And these are the results. 54 curves you see in this result over here. So let me walk you through this. We had 9 samples. Every sample has been illuminated with 2 different polarization. That makes it 18. So in every 18 cases, we had 3 curves for every 18 cases. 1 curve, experimental result. The other 2 curves, 2 theoretical results. One, a full wave simulation, the other one, circuit approach. So take a look at this color. Let's say this is 1 sample. And if you look at this one, for example, this red curve, you see 3 red curves over here. Shows the agreement quite nicely. Another sample would be this one, 3 curves over here. So you can see that these 3 curves with every color that you see over here agrees quite well. And this unequivocally showed that indeed these nanowires act as a lumped circuit element. Very clearly. And another interesting point, just like in electronics, that if you can choose different L and C next to each other, you can actually shift your band stop position. That's what happens over here. You notice as we choose different sample, it has a different width. That means different value for inductor. That means different resonant frequency. And you notice this dip actually moves over here predictably based on the circuit theory. So indeed, this acts as a circuit theory, as a circuit, lumped circuit element. And this actually was very encouraging to us. At the same time, this experiment showed that we have the stereo circuit. Because if we illuminate it with this polarization, it acts differently with the other one. So in the same experiment, we proved the two concepts. Right now, what we are doing, we are actually extending this concept to the indium tin oxide transparent conducting oxide in the near infrared. In the near infrared, ITO has a very interesting dispersion relation. Its permittivity crosses zero around 1.2 micron. So if we stay at the longer wavelength, like 1.5, 1.7, ITO should act as inductor at that wavelength. So that's what we are doing over here. So this is in collaboration with another colleague, Sherry Kagan, in our university. So our two postdocs working together. And what we have over here, we see that we have ITO and the gap. So that becomes effectively RLC that we have over here. And the preliminary result shows the very good agreement we have so far with the experiment. This is ongoing work to see that we are extending from the mid-IR now into the near-IR. Now, there are other analogies, by the way. I don't have time to go through all the specific analogy between electronics and photonics. But one thing in electronics that's quite interesting is wire. I mean, in electronics, we have wire. We take that for granted. But these wires that we have over here do a very important job. Actually control the flow of electrons from here to there. What is the equivalent of a wire in the Metatronic concept? We developed that concept too. And that also metamaterial will come to our help. So if you have a substrate made of material with epsilon near zero, and you cut grooves through this structure, that will actually confine the vector D around the structure, and that becomes a conduit for the displacement current. Now, I don't have time to go through the detail of that, but anybody interested, I'd be more than happy to talk to you about that. In fact, we experimentally verified that in my lab in the microwave domain. So we actually built this waveguide system with the fin, dielectric fin in between, and we bend the dielectric, and you look at how the electric field actually varies along this. So effectively, that becomes a wire, but the wire for the displacement current. Regular wire is a wire for the conduction current, with a flow of electrons. Here, we don't have a flow of electrons. Here, we have just vector D that goes in the direction we want over here. So it's quite interesting. It's just like a capacitor that you actually open the plates of a capacitor by like 4 free space wavelength in this case, 8 free space wavelength in this case, and still vector D follows the structure. It doesn't leak out. So with this tool in our hand, now we can go back into microwave and electronics and bring many of these concepts into the nanophotonics. So a filter to a filter. We just talked about that. So this is regular filter in electronics. This becomes Metatronic filters, in the mid-IR. How about antennas? So this was the antenna that Heinrich Hertz worked. But now we can have, of course, similar concept in the nanoscale. So what if you have 2 silver nanoparticles next to each other, and you connect it with the two metal plasmonic waveguides? Now, these two have very poor mismatch over here. So in other words, if you actually send a wave through here, most of it reflects back, because the impedances are not the same. But now that we have this lumped circuit concept in optics, we can actually go in microwave, find out how people do that matching, and then try to do the matching in the nanoscale. And in fact, here, if you put a nanoparticle over here, that nanoparticle is your matching circuit. So this is a simulation of this structure. You see the wave coming over here and very nicely radiates away. So you actually match a nano antenna to a nano waveguide over here. That actually quite interesting. Why? Because then we can actually have the concept of wireless link, but at the microscale, between 2 nano antennas. Now, in the microwave, you have tower and tower connection between this. There's no reason we cannot take this concept into the nanoscale. So what if we have point A and point B, micron separated, and you would like to connect this thing? You can connect it with the optical fiber. You can connect it with the plasmonic waveguide. Plasmonic waveguide would be lossy. So what we say is, why don't we call it plasmonic, but cut it and put an antenna over here, and let actually the free propagation of the light connects these two together. It turns out that actually becomes advantageous if you do that. The loss will be less because you don't go through the metal over here. So it becomes a wireless system, but wireless at the nanoscale. So the concept of Metatronics that we have introduced has interesting features. By putting the particle next to each other, you can actually design the distribution of your local optical electric field such that this will function as a circuit that you would have over here. So that means many of the design that the people have done in electronic circuit now can be brought into the photonics. I show you some of the examples that we've done, but there are many, many other examples that one can do. So I promise you that this way could be both ways. So now that you know you can make a nanostructure that has a specific filtering function, specific spectral information, that could be your building block to make metamaterial. After all, what is a metamaterial? Metamaterial is consistent of all these inclusions. Traditionally, people look at split ring, resonator, and so on to have that. But there's no reason that we restrict ourselves to those specific. So what happens if we start with this nanoscale filter and make many of those and put them next to each other? So effectively, that means like creating, in chemistry, you have this atom that has a specific, absorption band. So now what you can do, you can actually create this composite inclusion that have its own absorption band that you would design. So when you put this thing together, you would have a new metamaterial that have absorption bands that you like. So you specifically design the absorption band, so you create new materials with the specific absorption band that you want, creating this. So this analogy between electronics and metatronics, we talked about this, but these are all linear concepts. Right now in my group, we are doing nonlinear aspects of this. If we introduce nonlinearity to this, it becomes a tremendous amount of possibilities. I don't have time to go over that, but here, for example, is a 3 nano antenna concept that becomes equivalent of a mixer in electronics. So that becomes a metatronic mixer, very small. This would be in the order of, few hundred nanometer. Or what will happen if I have a filter that has variable capacitor with a Kerr structure? We are working at the 3-port network with the hope that one day we will have a transistor of this, if we can do that. Recently, we completed the design. We haven't published that yet, but we completed design of a particle that would work like a non-Foster circuits. In other words, a negative impedance converter, so to speak. Now, right now what we're doing is we're trying to extend this one into the visible domain. So one of the things we are planning to do is to have nanoparticle with the NSOM, try to measure the field over here, try to actually infer the impedance of that nanoparticle. Another thing we are doing is to see whether we can have a microwave system that has no metal. Imagine that. Imagine that we would have a microwave system that has no metal, but still has a resonances. So one of the things we are pursuing is that what would happen if these dielectrics would have a very high value of epsilon. In microwave, that's possible, and if we design it properly, you would have resonances that imitates the metal, but it's not really metallic. So far we studied what we can kind of learn from electronics and bring it in photonics. But this path is both ways as well. What if what we learn from here and we bring it back into electronics? Now, I mentioned to you at the beginning of my talk that conductivity is really a workforce behind electronics. But the problem with conductivity is usually that conductivity is a positive quantity, okay, because it's a passive structure. But if I look at metamaterial, or material in general, real part of epsilon could be positive or negative. Nature has given that to us. And with the metamaterial, we can make material that real part of mu could be positive or negative. Now, I cannot have sigma to be negative, because that would not be passive. But what if I have a material in which conductivity would be complex? Real part of it has to be positive, but I want that to be small, because I don't want to have loss. But imaginary part of it could be positive or negative. That would be interesting if we can have that in electronics, because then we would have this flexibility that we have in metamaterial. But do we have such a material whose conductivity is complex, whose real part of conductivity is small, and the imaginary part of its conductivity would be positive or negative? Yes, that material is graphene. It's a fascinating material. It's 1 atom thick structures that actually about 7 years ago, 2 scientists from University of Manchester were able to actually isolate them with 1 atomic thick structure, and those 2 scientists won the Nobel Prize just a year ago in 2010. It's a fascinating material. Thousands of papers been written on this, particularly in the electronic domain. But when I was reading some of those papers, I noticed something quite interesting, that usually people express graphene in terms of this conductivity. But as soon as I saw this formula, reminded me of something very simple. Admittance in circuit. Now we know admittance in circuit could be in terms of conductance and susceptance. So can we interpret the conductivity of graphene in terms of admittance and susceptance? Yes, if we can do that, then effectively what we have over here, we have back to RLC circuit. So in that case, graphene is actually an RLC circuit. Now, but this R relates to the real part of conductivity, and this L or C depends on this imaginary part, depending whether it's positive or negative. So if the conductivity of graphene has a positive imaginary part, that actually works as an inductor. If it has a negative imaginary part, that would act as a capacitor. That's quite interesting, because first let's take a look at the graph of this conductivity. There are many, many papers in literature written about conductivity of graphene. One very well-known formula and model is called Kubo's formula, which depends on frequency, chemical potential. By the way, this is not permeability. This is chemical potential, scattering of electrons, and temperature. If you plot the real and imaginary part of that formula, let's say for the chemical potential, you put some voltage across that, you notice that the real part is very, very small over here, non-zero, and then jumps at this frequency, and then imaginary part is like this. But look at this. Imaginary part can be positive and negative, according to that. So in this region, the graphene acts as an inductor. And in this region, graphene acts as a capacitor. But the beautiful aspects of graphene is that you can change this curve by just changing the chemical potential. And there are different ways of changing the chemical potential. You can put a voltage across the graphene, DC voltage, and you can change the... So if you change the chemical potential, you see how nicely you can change this plot. So if you stay at 30 terahertz, for example, you notice that the real part stays small, imaginary part could be negative, could be zero, could be positive. So very nicely you can tune this. Now, this can actually bring in interesting possibilities, and this is one of the things we are working on in the future, is that imagine that you have one sheet of 1 atom thick graphene, just one sheet, such that the real part of it is very small, and the imaginary part of that is under your control. If you control this patch, that the imaginary part is this one a different one, this one a different one, this one different, what if this section is positive, that's your inductor? What if this section is negative, that's your capacitor? So effectively what you have is a collection of RLCs, again. But this RLC is only 1 atom thick. It's the thinnest possible circuit you can think about. Thinnest possible circuit you have over here. And if you put the electrode over here, this works as a certain filter. You change the electrodes over here, it works as a different filter. Just like that stereo circuit that I mentioned to you, that the wave is coming from different direction. Here, it's actually electronic waves that is coming from different direction and works as a different filter. This is the one that we are working on that right now. And I don't have the result to show you over here, but this is one of our vision that we are working. But another interesting point, by the way, how do you actually make different region of graphene to have different conductivity? There are different proposals we have. You can put the voltage over here, and that would actually change the chemical potential, change the charge density over here, so as a result, change the conductivity. Or you can make, the spacer to be inhomogeneous. Or you can make the ground plane to be uneven. So these are the different techniques we are possibility that can be used in order to have a different section, a different conductivity. So let me go back, by the way, to this picture, and let me ask you a very simple question. If I look at the graphene, let's say if it's imaginary part positive, that means I have a bunch of inductors next to each other, and the air is capacitor. Now, what does this remind you of? Those of you in electrical engineering, this is familiar. It's a transmission line. And transmission line can have a wave along this. So does it mean if I have a graphene, I can actually have a surface wave along this graphene, hugging the graphene and propagating along this, which is known as surface plasmon polariton, SPP? The answer is yes. In fact, 3 authors before us proved that theoretically in their papers. So what these 3 guys showed, that indeed it's possible to have an electromagnetic surface wave hugging this 1 atom thick structure and propagating. And if you look at the wave number of that, the wave number follows this formula. You notice that the conductivity is in the denominator of this. So this term is much bigger than 1. So you can approximate that. So you notice that this beta is much bigger than the wave number in free space. Which means what? Which means this wave, actually its wavelength has been shrunk tremendously. So let me give you an example. If we are operating at 30 terahertz, which is 10 micron wavelength in free space, CO2 laser, and you can couple that into this graphene, you get a wave that has the wavelength of 144 nanometer. Now the frequency is still 30 terahertz. So the photon energy is still the same photon energy, but the wavelength has been shrunk 70 times. Now that actually gives us a lot of possibility. That means you can actually squeeze the wave and you can actually have a very important sub-wavelength feature detected by this. You don't need to be in the near field. You just need to be on the graphene to do that. So that actually inspired us to look at many interesting optical devices. So imagine that I have one layer of graphene that intentionally I make the two region of that to be two different conductivity. Just like two different voltage I put over here. If I do that, for example, this is from Kubo's formula, we put the number there. Intentionally we choose it such that the real part is very small, imaginary part opposite sign, different numbers. Now, when it is positive, it can support that surface wave. When it is negative, it can support another surface wave which is not that highly confined. So basically it doesn't support anything. So what happens if I excite this graphene? This is the top view of our simulation. In the region that can support, this surface wave is coming over here, and then it cannot support anything over here. What happens to that surface wave? Reflects back. So it's a Fresnel reflection, but it's a Fresnel reflection only on one atom thick. So you have a 90 degrees, reflection on one atom thick structure. Now if we can have that, then we can have a lot of interesting possibilities. You can have optical waveguide. You can have optical fibers. All of them one atom thick. So that would be the thinnest possible waveguide you can think about. So thinnest possible wave. By the way, one thing I forgot to mention, that this surface wave that you see over here is highly confined to this structure. So the field that's coming out of it is actually exponentially decaying about 20 nanometer. So the entire range of the wave is 40 nanometer across this. And because it's highly confined, it cannot be radiated away. So when it sees the discontinuity, it actually stays in this structure. So you can have a bending waveguide, you can have things like this, you can have a guided waveguide, you can have a splitter. So many of the devices can be brought into one atom thick structure. You can have metamaterial, you can have the entire concept of metamaterial in one atom thick. And you can have lensing system on one atom thick. So what if I put the wave over here and I create different conductivity over here. So this looks like a lens. When this one coming over here is going to focus at this point. So that means what? That means if I start from a point, it gives me a line. If I move this point over here, it gives me a wave in that direction. What does that remind you of? Fourier transforming. So this one atom thick structure can do Fourier transforming. It can do optical signal processing, which is only one atom thick. So that means if I have stack of these guys on top of each other, only 100 nanometers away from each other, you can have a massively parallel optical processors that's going on over here. Only one atom thick structure, and actually the loss is relatively low, so this can go actually like 15 times SPP wavelength, which means it's only about 1.5, 2 micron. So within 1.5, 2 micron, you can do this processing. You have that. So, by the way, how much time do I have? I can tell me.
4 o'clock now.
Should I stop? Yeah, okay. So let me just go back. Okay. Let me just. So this last topic that I wanted to talk about is basically extending this concept into controlling the flow of the electrons. Controlling the flow of the electrons is that in electronics, you can control the flow of electrons because you put the voltage over here, you go like this. In photonics, we cannot do that because photons don't have charges. But you can create unreciprocal metamaterials that would allow the photon to go only one way, not the other way. So anybody interested, I'd be happy to show you those few more slides later on. But let me just show you the summary. At the beginning of my talk, I showed you this slide. And I said that these parameters actually basically is a force behind these technologies, and these technologies evolve separately. But I hope I've been able to convince you over here that if you look at this one in a more embracing way, as a metamaterial and connection between this, we don't need to look at these structures separately. We don't need to look at these fields separately, but we can look at them in ensemble. And that's what I call it Metatronics over here, to really bring all of this together. And when we have this new mindset, we can come out with the interesting devices and components that some of them I showed you over here. And with that, I thank you very much for your attention. Thank you.
Time for a couple of questions. Get exercise.
Hi, Nader. Thank you very much. It was a great talk. I really
Thank you.
appreciate it. Question about the graphene. How fast can you switch that voltage? Can you use that to do like a modulation process and things of that sort?
Good question. I don't know the answer to that question yet. That's a very good question. Remember that the voltage, the capacitance is not necessarily that much, so I anticipate that could be fast, although I don't know the answer to that yet. But one way is that you can have a voltage over here, you can have another volt, if this is split at this point. So you can have split gate, but if you want to have more kind of segmentation, then you better do it with the ground plane. So if you have a ground plane uneven, and you put this fixed voltage over here, the electric field would be distributed unevenly, charge distribution would be uneven, and the conductivity would be uneven. So how fast you can change that, that's a good question. That's something we're going to look into that. I don't have the number for you for that. But that could be quite interesting. Yeah. So you can actually quickly switch it, doing the Fourier transforming, do something else. Absolutely. Absolutely. Yes. Thank you, John. Yes.
The memory effect. And so do you have this, have you thought about this?
Yes, we have done something on it. We haven't published that yet, but we have done something on it. Although the reason we haven't published that because we want to actually study that more to see whether it has a complete, effect of the memory store or not. We have got it in our theory of that memory store. We have got that kind of like a figure of 8 type of thing. But we still want to work on it more in order to see whether it has a memory effect or not. So we have gone part of it, but we don't have the complete picture of that yet. But instead of that, one of the things we are more interested than memristor is to actually have a 3-port element. That's even more, in my opinion, more relevant. Because then I can have switching. If I can have switching with the displacement current, that would be even more relevant. But yes, but I can talk to you about what we have obtained so far on the memristor. Yes.
Can you comment on how to efficient couple from like fiber or other free space to graphene?
Excellent point. Excellent question. Remember I mentioned that the free space wavelength is about 70 times different than the wavelength on the graphene. In one sense, that's a good thing, because then you can squeeze this wave over here. On the other hand, coupling becomes an issue, because you have to couple to something that is 70 times different for that. One way that we have done the simulation of that is the following. That we got the graphene and we put, metallic nanowires underneath of this, not touching the graphene, but about 10 nanometer underneath. And the separation between nanowires we actually calculated based on the lambda SPP of that surface wave. And we send the incident plane wave through it. Now, incident plane wave go through the graphene very nicely, because only one atom thick. But when it hits those nanowires in the near field, it gets coupling into the system. So far, we have found that if you have 4 or 5 nanowires, you have about 4 to 5% coupling. Probably you can increase that. But 4 to 5% is pretty good. It's doable. So this was actually to answer to the question that, often people ask me that, how do you couple that? So we did this simulation to show whether it's feasible or not, and it appears to be feasible.
Let's thank our speaker once again.
Thank you. Thank you very much.
So there's a reception.